Consider a plane pi1 and a point A in space. We will derive the formula to find the perpendicular distance between point A and a plane pi1 in both vector and Cartesian forms. Let us start with the vector form. Let vector A be the position vector of point A with respect to the origin. Consider the normal form of the equation of plane pi1 given by equation 1. Distance d in the equation is the perpendicular distance ON1 of plane pi1 from the origin in the direction of unit vector n. Now consider another plane pi2 parallel to plane pi1 passing through point A. Since plane pi2 is parallel to plane pi1, unit vector n, that is perpendicular to plane pi1, is also perpendicular to plane pi2. Thus the equation of plane pi2 perpendicular to vector n and passing through a point with position vector A is given by equation 2. Simplifying equation 2, we get equation 3. Comparing equation 3 with the standard normal form of the equation of a plane, we find that perpendicular distance ON2 of plane pi2 from the origin is given by equation 4. Let us draw a perpendicular from point A meeting plane pi1 at point B. The distance of point A from plane pi1 is equal to distance AB. Since the planes are parallel, all perpendiculars between them will have the same length. Thus, distance AB is equal to distance N2 N1. Distance N2 N1 is equal to distance ON1 minus distance ON2. Next, we substitute the values of distances ON1 and ON2 from equations 1 and 4 in the previous equation. Equation 5 gives us the formula for the distance of a point with position vector A from a plane at a perpendicular distance d from the origin. Now, let us look at two special cases. In the first case, let the equation of plane pi1 be given in terms of its normal vector n and distance d from the origin. If the equation of plane pi1 is of the form shown, distance AB is given by equation 6. In the second case, we consider the scenario when point A coincides with the origin. When point A coincides with the origin, its position vector A becomes 0. Substituting vector A as 0 in equation 6, we get equation 7, which gives the perpendicular distance of the plane from the origin. Now, let us derive the equation for the distance of point A from the plane pi1 in Cartesian form. Let the coordinates of point A be x1, y1, z1. Thus we can write the position vector of point A as shown. Similarly, if the equation of plane pi1 is given in Cartesian form, the normal vector n to the plane can be written as shown. Substituting the values of position vector A and normal vector n in equation 6, we get equation 8 that gives the perpendicular distance of point A from plane pi1. Consider a plane pi and a line L as shown. We will derive an equation to find the angle between them. Let vector n be normal to the given plane. Let the angle between the given line and the normal to the given plane be theta. Let the angle between the given line and the given plane be phi. Angles theta and pi are complementary angles. Thus, the angle between a line and a plane is complementary to the angle between the line and the normal to the plane. Let the equation of the given line L be as shown. Also, let the equation of the given plane be in the normal form as shown. Then, angle theta between the given line and the normal to the plane is given by equation 1. Since theta and phi are complementary angles, cos theta is equal to sin phi. Thus, we can replace cos theta by sin phi in equation 1. Thus, angle phi between line L and plane pi is given by equation 2 as shown.